Am I audible?
Yes, Dimpa, you are audible.
Okay, thank you, ma'am. I am Dimpa Kalita, lecturer at the Department of Civil Engineering. I am the moderator for today's webinar. I'd like to welcome Professor Dr. S.P. Singh, Sir, Vice Chancellor, Royal Global University, Professor Dr. Alok Kumar Boragohai, Sir, Chairperson Economics, Dr. Arnab Sir, Head of the Department, Civil Engineering, and Speaker Dr. Hemant B. Kaushik, Sir, Professor and Head, Center of Educational Technology, IIT Guwahati. All the participants to our departmental webinar on the risk M6.4 Assam earthquake and its lessons. Well, I have been associated with the Assam Royal Global University since January 2020, the very institution which has efficiently attained its successful initiation as a university is already the choice of many aspirants for higher education. Royal Global University, guided by its vision and mission, is already standing strong, global contributor in the education scenario of the nation. Over the years, it has efficiently grown in terms of size and stature, and as of now, Royal Global University has 27 schools in different disciplines offering a variety of courses. It is a blessing for the RGO fraternity that things has gone the way it was planned. God permitting, that day is not too far when the university prepares the next generation to lead and make a significant difference in the world. At this juncture of crisis, when the entire planet is dealing with hindrance and confinements, Royal Global University stands tall in imparting quality learning via different digital platforms and organizing webinar series, with the sole motto of keeping abreast with the latest technology and challenges to cope with the pandemic. Today, we are extremely privileged to have amongst us Dr. Hemant B. Kaushik, Professor and Head, Center of Educational Technology, IIT Guwahati, as our eminent speaker for today's webinar. Professor Kaushik postgraduated in Structural Engineering from Vishwesvaraya Regional College of Civil Engineering, Nagpur, and obtained PhD from Indian Institute of Technology, Kanpur. Followed his civil engineering career in 1996 as a project engineer at Tunnel Builders, Nagpur, before joining as an assistant professor in the Department of Civil Engineering, IIT Guwahati, back in 2007. Sir was associated with IIT Kanpur as a senior project scientist. Currently, he is the professor in the Department of Civil Engineering and head of the Center of Educational Technology, IIT Guwahati. His area of interest mainly encompasses earthquake-resistant design and nonlinear behavior of structures. Sir has been relentless in the field of seismic vulnerability assessment of structure, earthquake damage survey, and retrofitting. He is a member of different professional bodies that includes Earthquake Engineering Sectional Committee, Bureau of Indian Standards, Earthquake Engineering Research Institute, USA, American Society of Civil Engineers, USA, Indian Society of Earthquake Technology, India, and many more. So, as a stalwart in the field of earthquake-resistant design, it is an honor for me to welcome you, sir, in our webinar. The platform is yours, and we are eagerly waiting to hear from you.
Thank you, Dimpa, for the nice introduction. So can I start now?
Yes, sir, you can start, sir.
Okay. So first of all, thank you, Royal Global University, for inviting me to this talk on the recent Sonitpur earthquake that took place on 28th of April. So what we will do today, initially I will just glance all of you through some of the damages that have occurred during the earthquake, and then we will try to see what lessons we can learn, not only from this earthquake, but also from the past earthquakes in India and neighboring countries. So it happened on 28th of April, early in the morning at 7:51 a.m. for about 30 seconds. And these 30 seconds were actually terrifying moments for a lot of us, for many of us. Not because we were surprised, but because we were already under the stress coming from this COVID 19 pandemic, and also because the lockdown, the partial lockdown has just started, and we were all of us we were in our homes. These schools were closed, so most of the people were actually inside their homes at that time. The National Center for Seismology, it identified the magnitude as 6.4 on the moment's magnitude scale. The epicenter was just about 11 kilometers from Dikyajuli and about 75 kilometers from Guwahati. The National Center also identified the depth as 17 kilometers, which is termed as shallow. There is a small difference in the magnitude given by the USGS. They say that it is 6.0 with slightly varying epicenter, almost similar epicenter, but the depth is almost double. And USGS also identified the intensity, the maximum intensity on MMI scale to be about 7. That is the maximum intensity of 7 on MMI scale. There are no casualties directly related to the structural failure, but there were two elderly people suffered heart attacks and they died during the earthquake shaking. So this is the isoseismal maps during the shaking. So as you can see here, the town of Dekiajuli here in the Sonitpur district. So this is the epicenter, and you can see the maximum intensity of shaking of 7 here. So this scale here on the right top corner gives you the intensity along with the barcode, along the color code here. Here is the Guwahati. The maximum intensity of shaking in Guwahati was about 5 to 6, mostly 5. All of you know that when you go towards the epicenter, the intensity increases. That means the damage, expected damage increases as we move towards the epicenter. So this is a map given by the USGS. The earthquake was felt not only in India, but in the neighboring countries of Bangladesh, Bhutan, China, and Myanmar. And there are reports from all over these countries, even Nepal as well, that people felt the earthquake shaking. Not only the main earthquake, but also some of the bigger aftershocks. So 13 aftershocks were felt in just next 3 days. These aftershocks were all having magnitude 3.0. So I'm not counting the aftershocks having magnitude less than 3.0. And yesterday also there was an aftershock that was felt even in Guwahati. Out of these 13, two were having of magnitude more than 4.0. And even during these aftershocks, people were frightened. So these are the locations of these epicentral locations for these aftershocks. So spreaded all over, all around the, I'm sorry, spreaded all over uh, around the epicenter. Now, as soon as the main event struck, immediately we had two aftershocks. So the people who came out of their houses, they some of them actually waited for a long time because of the shock, because of the fear. So that this is normally normal in case of big earthquakes of magnitude 6 and more, that we get so many aftershocks. In fact, the some of the bigger earthquakes had even thousands of aftershocks after the main event. So this is quite normal. And we heard many stories, many news, many predictions that day after tomorrow or tomorrow at this time we'll have a bigger earthquake. So these are all rumors. We cannot predict the earthquakes. We all know how and why these earthquakes are occurring. So our Indo-Australian plate is actually colliding with the Eurasian plate. It is our plate is going down the Eurasian plate, and that's why we have these Himalayas along our northeastern boundary. And because of this subduction zone, there are many faults, there are fissures, because of which we have a very complex geological scenario here, and this earthquake is one of them. What are the effects of shaking? Well, as far as uh, the news reports are concerned, the the part of these Bhairavkund hills near the Udalguri, they collapsed. This part of hill collapsed during the earthquake shaking. Now, for me, this is the biggest damage that one could observe here in this earthquake. Then there were big ground cracks and liquefaction near the epicentral region. Again, this is also a significant geotechnical issue that needs to be addressed. It has to be studied again why such huge ground cracks occurred there, why liquefaction. And then there are videos which are viral on the social media showing water coming out of the ground with so much of force. So this requires a detailed investigation from different stakeholders. One building in Nagaon, it tilted and it was supporting on the right, this bigger building. Now, obviously, there is no other damage. You can see there is no other damage to the building, but simply tilting, that means there was some settlement, there is some problem with the foundation. I don't know what type of foundation was there, but obviously there was a problem with the foundation, with the soil here in this building. Now, this building is about 40 to 45 kilometers from the epicenter. Not very far, but still, it is not in the mesoseismal region of highest expected damage. Then the other damages because of these earthquakes, you can see here the masonry infill walls failing, the huge crack in the infill wall, and then finally it collapsed in the out of plane direction. Then the famous hotel, all of you know these pictures, these cladding fails. So these are all non-structural damages. These are not my photographs I've taken from the news media. The parapet walls, boundary walls, again masonry walls that fail in the out of plane direction. So it is not very difficult actually to prevent such failure, but then somehow the uh, engineering judgment required to protect these walls was not there. Masonry infill failure is a very common, very expected failure, much expected failure in any earthquake, even of smaller magnitude. The reason is very simple, that these earthquake waves, they are basically energy waves, and this energy has to be transmitted, has to be dissipated somewhere. So these masonry infill walls, they dissipate the energy. And if we can construct our reinforced concrete members properly, such that this damage in masonry does not result in damage in RC columns and beams, then we are safe. Then we have successful in our design. Now it is only a question that whether we are doing this, correctly. So this is a long wall, you can see masonry infill wall. And obviously in long walls, we always see such kind of shear failure. X types of cracks are very commonly observed. So here also, same building, you have the X cracking in the masonry infill wall. Again, a long wall. And what you can see here is that there is a thick plaster on the walls. And not only the plaster, but above this plaster, there was a plaster of Paris. So we are actually trying to showcase as if the construction is really nice, the finishing is really top class, but then what actually matters is not the top finishing, but the structure itself. So this is not a serious failure, but then what I'm showing you is what kind of failure was there during the earthquake. These are all repairable easily. Again, the failure of masonry infill wall. So you can see how the energy is actually dissipated by these infill walls. So if properly constructed, if we can avoid the out of plane failure, if we can avoid such big removal of the plaster, then we can actually save the buildings. Collapses of the false ceilings is another commonly observed failure during this earthquake. Hundreds of buildings, I could get reports that such false ceilings have failed. The primary reason was the construction was not proper. This was not a big earthquake where we expect such kind of false ceiling failure, but then because of certain issues, minor issues, the ties that connecting these claddings to the ceiling were not proper. So this issue can be handled very easily. Now, though it may appear to be a non-structural failure, but just imagine the whole false ceiling falling down and someone is working in the cubicle here. Luckily, it was 7:51 in the morning. No one was working here, but so otherwise you could have big damage. Look at this non-structural damage. Now, was it so difficult to avoid? Can't we provide suitable arrangement for this water purifier here such that it does not fall down? So this is what I'm mentioning. These are the failure, these are the damages that we can actually very easily avoid. One interesting aspect is during this earthquake, most of the reported damage was in reinforced concrete buildings. I have at least not come, I've not read any news. Nobody has informed me that any damage has occurred to any other structure than the reinforced concrete buildings. So there are certain questions that come to my mind. Are we designing and detailing these RC buildings properly? Are we providing masonry infill walls properly? Are we using the design codes properly? So these are some of the questions that our young generation have to think before actually designing and constructing any buildings. So finally, there is a significant geotechnical issue that we have seen. There are huge ground cracks, the hills failing, liquefaction. So these issues are more in this present earthquake. Now, most of the reported damage is non-structural. So the parapet walls, the boundary walls, false ceilings, these are non-structural, but that does not mean that they may not result in casualties. They can. We were lucky this time that the timing was such that there was no casualty. Another major issue with such non-structural damage is this takes a toll on the economy of the system. So, for example, some of the buildings, big buildings that I visited after the earthquakes were shut after the earthquake because of such non-structural damages. People were not ready to go inside, and how can they when the whole false ceilings have fallen down? So it takes a toll on economy, right? So even though there is no casualty, but then there was a loss, economic loss, huge economic loss to many businesses. Then major damage to masonry infill walls, minor cracking reported in some reinforced concrete members. Initially, there were reports that huge damage has occurred to some reinforced concrete members in some buildings, but then later it was clear that the damage was actually not in the uh, real concrete of these members, but in the plaster. But still, there was some minor cracking reported. So why? I mean, during the 6.4 magnitude earthquake, I mean, this is a big earthquake by any standard. So why there was no major damage? This is the common question that people ask. So earthquake characteristics are responsible because of certain earthquake characteristics. There was no damage. Maybe because the earthquake was slightly deeper. If you go with the USGS data, it was about 34 kilometers. The earthquake has very high frequency, so it may be another reason. So the frequency filtered out in different topology as it moved away from the focus. There is a low population in the mesoseismal area. So near the epicenter, the population is not much. Or we were lucky, maybe. But what is important is what could have happened. So those of you who have studied earthquake engineering or are studying, they know that with every single uh, number increase in the magnitude, I mean from 6 to 7 or from 5 to 6, there's a huge increase in the energy released during the earthquake. So from 6 to 7 magnitude, the energy released is 13 times. And the amplitude of the shaking is about 10 times increased. So what could have happened? And even with the same magnitude, if the duration is more by about 10 seconds, what could have happened? So what luckily we have avoided. Let us discuss those issues. Before that, we all know that the seismic hazard is maximum in this region. The entire Northeast comes under high seismic hazard. This is as per ISO 893 2016. Now, maximum intensity, expected intensity in this region is 9 or more, right? So we have to design our structures for this intensity. And you can imagine what will happen when this big earthquake occurs, even if we are not able to actually design properly for the smaller earthquakes. The frequent earthquakes are expected in Assam, and we have been witnessing these smaller earthquakes. And the smaller the earthquake, the frequency will be higher. Bigger earthquake will have, of course, lesser frequency. So we expect bigger earthquakes, but not so frequently. So this was one of those bigger, but maybe like we discussed in the previous slide, there were certain reasons why the damage was not much. Now, I'm surprised that people are surprised with the intensity of the shaking, but we should not be surprised because this is expected in this region. So here we'll discuss what happened in the past, where are we in the present, and where are we moving towards. We have been using masonry since ages. I mean, you can see the structures which are hundreds of years old and still standing. For example, this building here is a cellular jail constructed purely of masonry in Port Blair. It's a huge structure. It's a tourist attraction now. You can still go, but about 110 years back, British they use this structure as a kalapani. So they used to send the prisoners from the mainland India to the Andamans. So we have been constructing this masonry beautifully and properly since hundreds of years, maybe 1,000 years. And interestingly, more than 80% of the building stocks in India presently are such buildings, the unreinforced masonry buildings. So when people say that we have reinforced concrete high-rise structures, we are only talking about maybe 10% or 15% of the structures in India, that's all. But most of our structures are unreinforced masonry buildings, 80% and more. So we are talking about semi-urban rural areas here, where most of our population uh, stay. We somehow have a habit of using masonry in our structures, right? You show me a structure in India in which masonry is not used, and I'll be surprised. Why is it? Because it is easily available, it is economical, and it has many other advantages that it is strong, then it has good sound and heat insulation. So we can very easily use them and in a variety of manner. That's why I'm saying that properly built masonry buildings have been performing well since several decades, but then those masons are not here nowadays. Now the kind of masonry buildings we are constructing are very poor. Now where are we presently? We recently have developed an obsession with the reinforced concrete buildings. Somehow all of us want to live in reinforced concrete buildings, right? And then, like I already said, we have a habit of using masonry. Then we use poor material to save some money. We don't use our design codes. So finally, what we get is our very hybrid type of irregular structures. So this poor Superman here is trying to actually prevent the failure of these open ground story buildings. Right? So earthquakes don't kill people, but unsafe buildings can kill people. So this is what is meant by here. So these irregular structures, they are responsible for very high seismic risk in the region. And you can see so many irregular structures here. So this photograph here, it shows a very similar type of failure, right? The type of failure that the Superman is trying to avoid is shown in this photograph here. This is from Turkey, 1999 earthquake. So what do we do? So before we can even try and think what do we do, let me tell you that we are not even able to design, detail and construct simple regular reinforced concrete buildings properly. Now look at these examples here. Is this the way we construct the reinforced concrete beams and columns? So this is a recently constructed building, and you can see what I don't know whether you can call it honeycombing because I don't see concrete at all. Then you see here, these walls actually before failure, they have damaged the columns. So simple uh, location of openings actually could have reduced this type of damage. Look at this intermediate failure of this floor. Otherwise, the building is standing properly. So, what to do with this building? There's no other choice but to dismantle this. So you can see here dismantling activity already going on, right? And the material debris is falling here. Look at this building, regular building, not very tall, no open ground story, but it collapsed. Okay, so this is what I'm saying, that we are not actually designing our reinforced concrete buildings. We are not detailing them properly. Can you see here in this building? Can you see in this 600 mm, there is no stirrup, right? And all of us know that this is the region where we expect the plastic hinge to develop during the earthquake, where we expect some damage. And there is no stirrup here, there is no shear reinforcement. Then you see how polished this section is. We construct this column up to this point, and then this part of the column is constructed along with the slab. So there's a clear-cut joint here. So these are simple things that we are not able to do. Now, if this is the status of regular buildings, what will happen to the complex, irregular reinforced concrete buildings? Because all of us love complexity. All of us love irregularities. Let us see what happens. So the biggest problem in Indian cities, in urban cities in India, are the open ground story buildings. So this is the irregularity, the vertical irregularity that comes because of absence of the masonry infill walls in the ground floor. So if I apply a lateral load at the top of this building, so you can see here there are two parts to this building. The left part has open ground story building. The right part does not. Okay. Now let us see how this building is going to deform because of application of this lateral loading. So these are all the floors of this building, and I'll show you how typical deformation will be visible when I remove the masonry infill walls entirely. So now I'm assuming that there is no infill wall anywhere along the height of the building. So in that case, if I apply this lateral load at the top, I will get a very beautifully well distributed lateral deformation along the height of the building. So this is the bare frame. So you can see that here, if I take this displacement, relative displacement between these 2 points versus relative displacement between these 2 points, so inter-story drift ratio, it is more or less constant from top to bottom. And this is how our building should behave. Now, if I consider this right-hand side building where the infill walls are there in all the stories. So this is fully infill frame. And obviously, because of presence of these infill walls, you will find that the deformations will reduce, right? So from this point, it has reduced to this point. And even then, the vertical deformation profile is quite regular. So inter-story drift ratio, again, they're more or less similar when you go from bottom to top. Now, very interesting feature of this open ground story or open first story frame. So this building, the real building here. Here you can see that the most of the lateral deformation is actually accumulated in the ground floor itself. And the vertical stories are not deforming much. So they are more or less constant, slight deformation. But look at this deformation here. So obviously our columns here, they will not be able to accommodate such a big rotation, such big deformations, because they need to have very large ductility demand in these columns. And it is impossible to actually provide such large ductilities because of the limited size of the columns that we provide there. Unless we have reinforced concrete walls or even infill walls that can prevent such kind of large ductility demand, we cannot design these columns. So this is a major problem with the open ground story buildings. And because of this problem, you see, in every earthquake that has occurred in India in last 25 years, such buildings have collapsed. So I'm showing you the photographs from 1997 here. I heard this news. I did not visit this area, but then I heard the news. But the team from IIT Kanpur, they visited And when I joined my PhD in IIT Kanpur, I got this photograph. So 22 May 1997, small earthquake 5.7, and we have such kind of a open ground story failure. 2001 Bhuj earthquake, this is a famous photograph. All of you know about this building. It's 5-story, but now only 4 stories are visible. The open ground story has gone. 2004 Sumatra earthquake. So this building is only 2-story, right? And you can even see the car here. So the parking space which was constructed for this car, neither the car can be used nor the parking space now. And look at the building, look at the quality of concrete. Only 2-story building and completely collapsed. This building was about 1,000 to 1,100 kilometers away from the epicenter. The epicenter was in Indonesia, Sumatra. But the earthquake was so big, 9.1, that the buildings have collapsed in Port Blair. 2011 Sikkim earthquake. It was again a big earthquake, 6.9 magnitude, and you can see open ground story building failure here. So there were several such columns which have failed, but the complete failure of these buildings was avoided. 2015 Nepal earthquake, again a big earthquake, 7.8. So this building collapsed. Now this is, though it is an open ground story building, but then it was not the only reason why this building collapsed. There were other reasons because of soil subsidence, because of the slopy ground. So there were many problems here. 2016 Imphal earthquake. This was not even a completely open ground story building. It was a partially open ground story building. And you can see when such failures occur, there is no other way to retrofit or to strengthen this building. You have to dismantle it. You have to completely remove the building. And you see, this dismantling will take a lot of time, effort, and money. Now in Assam, we have thousands of open ground story buildings, and there were reports that from some about 15 to 20 buildings, some damage was there in these buildings in Guwahati city, only Guwahati city I'm talking about. But some engineers, the Assam State Disaster Management Authority, and some local engineers, they have actually tried to improve the size of the columns by jacketing. But I have myself not seen those columns. I've only heard them. Now, these are some of the common problems that we can think of. So first, it is the irregularities in the structure. So most importantly, the vertical irregularities, the open ground story buildings, but also the horizontal irregularity, the irregularities in the plan related to torsion. Those are also very severe. Non-involvement of engineers, this is a big problem in India, not only in this part of our country, but everywhere. I can cite you one very interesting story of my PhD student whose parents were constructing a house in Guwahati city. And then when this student started giving them advice about ductile detailing, about the sizes of the columns, they started not discussing the issue with the student, right? The because of requirement of more money. So, but then if you really look at it, it does not take much money to provide ductile detailing. Rather, most of us spend more money in beautification of our toilet blocks, in our tiling system, in cladding. So instead of that, if you can spend some money on improving the design and detailing, that will help. Non-adherence to the design codes, of course, same thing. People think that if we do this, time and money will be wasted, but it is not so. Poor choice of construction material, again, it has 2 points. First, availability is one issue. Sometimes the good material is not available, for example, the sand, cement. But then sometimes it is also about saving money. Poor workmanship, so we don't have skilled laborers, we don't have skilled masons because we generally don't use them because we need to pay more to them. So everything boils down finally to saving money, saving time. And very interesting problem is that we have some perception that every building has to be a reinforced concrete building. I don't understand the reason why. Can't we construct small family dwellings using vernacular housing systems? If you look at other countries, And why should we look at other countries? We are such a great nation. Because we always look at other countries that America is doing this, Japan is doing this, Australia is doing this. So let us look at the examples of other countries. In California, which has highest seismicity, some of the highest seismicity in the world, you will not find a single family house constructed of reinforced concrete or even of structural steel. Almost all houses in these seismically prone areas are wooden houses, right? In Japan, in New Zealand, you will find most of the houses that individual family builds are not reinforced concrete. So, are these the solution to these problems? Let us see. Now, because of limited time, I will shortly discuss these two vernacular housing systems. First, you already know it's such a famous typology, not only in Assam but in the entire world. People really appreciate the kind of uh, uh, connections used in these houses, the type of material used in these houses. I'll show you some details later. But before that, when I joined IIT Guwahati, I started working on a project, and with the help of my MTech student, I wrote a very simple World Housing Encyclopedia report on these Assam type houses. And you'll be surprised to know that this report has been downloaded by about 10,000 people in the entire world, which is surprising because people actually are still interested in learning how different vernacular housing systems are constructed in seismically active regions. But somehow we have forgotten such buildings. We have moved from these buildings to some other types of uh, structures because of our obsession with other materials. There's no problem with that. We can be obsessed with some material, we can move to some other material, but then the problem is we have to also learn how to use that material properly, how to design them. We are not somehow doing that. The second type of houses that we will discuss today is the confined masonry houses. So some of you, I hope some of you know what are confined masonry houses, but to them who don't know, we will discuss in brief. Now these are single wall of Assam type house. I'm sure you all know about this, so I'll not spend much time. So it has these wooden members. So main members here and these secondary wooden elements which actually share the load. And then there is a masonry wall at the bottom up to sill level. We have these ikra walls above the sill level. See, the connection is really interesting. These are the sizes of all these members, the main members, main post, and the horizontal and vertical studs. Let us look at the connections. These are really interesting. So this is a joint A, this joint here, this joint B. So these two joints, they are very similar, but then there is a very interesting difference here. So the steel L clamp is provided in perpendicular directions. So this steel L clamp here, it resists the rotation at the bottom, joint A, but the steel L clamp at joint B does not resist. So so there's a stability that is provided by a combination of these, plus there's slight stiffness and strength that is also provided by these joints A and B. This is joint C. Again, it's open mortise and tenon joint, very flexible joint. Joint D is a mortise and tenon joint. So these are joint D here. And look at the connection. It's only by mortise and tenon. And then with the single uh, nail, they make the connection. Joint E, it is a projecting wedge groove kind of arrangement that we provide. And you can see here that joint E is provided in the diagonally opposite directions. Joint D is provided in the diagonally opposite ends. And finally, the joint F, this is the internal joint, which is again the vertical stud is simply we create a tooth and provide it in the horizontal stud groove. So the basic, the basic idea here is to provide more flexibility to the system by not having rigid joints. So all these joints are very flexible. So we carried out a lot of tests on these individual joints all joints A, B, C, D, E, F. So every joint we tested, every member we tested, and then we also tested the whole house of this Assam type uh, buildings. So this is a single story, single room house which was constructed over the shake table at IIT Guwahati. And then we applied in a single day, we applied about 112 ground motions on this house, single house specimen. And you will be surprised to know that even after application of these 112 ground motions, there was no damage at all to this house. I hope this video works here. Let me see. Yeah. So this is the Taft ground motion. The peak ground acceleration was about 1 g. And you can see it's not a very small earthquake. Peak ground acceleration of 1 g is a big earthquake. Some people say that the peak ground acceleration of 28 April earthquake in Assam was about zero 0.1 to 0.15 g only. So this was about 10 times higher. And the student who did the test is standing here, Biswajit Chand. He has completed his PhD on this topic. Now, even after subjected to this big earthquake, you cannot see any damage here, right? And why should I show you this video? Because you all have seen these Assam type houses since so many years. And you know that there is no damage to these houses even during big earthquakes, right? So this is just one shaking that I'm showing you. We applied 112 such shakings, and we could not fail this house. So what we decided at that time, because student was really um, disappointed because he wanted to fail the structure. So what we decided then, we will push this structure and pull this structure on a different test setup and try to fail it. So this is another setup where the same house we shifted at IIT Guwahati lab, and then just see here we are applying the push and pull load. And this was applied by about 250 plus minus displacement. So you can see if you can what happens to these joints here. These are all flexible, right? And you can see here the displacement that we have applied at the top. So we have already applied about 30 mm displacement. This test is I'm showing you is a very fast forward manner, not real time, because real time taken during the test was about 2.5 hours to 3 hours, but I'm showing you it in about a minute. So this is about 85 mm, which is huge actually. And you can see the separation of these ICRA panels from the surrounding frame. You can see here the separation of this joint. Every joint actually is so flexible that it is simply separating. But then it is also going back there. We have already reached 150 mm plus minus displacement here, which is again very huge displacement. And you can see here now there is a slightly you can see the ICRA panels, the bamboo shoots inside this plaster. And you can see the groove and wedge arrangement here, which is separating and but again joining. We reached 220 mm. And remember, this such kind of displacements are not seen during earthquakes. So 240, 250 mm displacement, and we could not fail the structure. So then we removed such kind of arrangement. We provided another arrangement in which we pushed this structure on a single side by about 500 mm. We did not pull it, we simply kept on pushing it. Okay. Then we could actually fail some of the walls. So 500 mm displacement is not less for a single story structure. Right. So we all of us have seen such beautiful uh, behavior and performance of Assam type houses. Let us see some of the behavior of these confined masonry houses. But before that, those of you who don't understand what is confined masonry, here is the difference. Uh, there is a difference in the construction process. So in confined masonry, we construct the walls first. So there's a foundation, and then we construct the wall. After that, we construct these tie columns and the tie beams. In reinforced concrete, we construct the RC frame first, and then the infill walls. The load transfer arrangement is different. we'll discuss this, the structural system becomes completely different, and there is a lot of saving in the cost if we are doing confined masonry. Now, you look here, if we have the infill wall or the reinforced concrete frame with infill wall, this masonry wall is not designed to carry the vertical load, and we don't bother whether it carries lateral earthquake load or not. So the only reason this infill wall is there is to fill this gap. Otherwise, it has no structural design. It has no meaning otherwise. So we are wasting this material simply. And without knowing that during the earthquake, this masonry wall actually resists a lot of load. And since we don't realize that, we don't design them properly. And that is the whole problem. On the other hand, if you consider the confined masonry wall here, we design this wall to resist all types of loads. The vertical load coming from the upper floors, the lateral load coming from the earthquake. So this wall is expected to resist all loads. So what is the role of this column and beam? So first of all, we don't call them columns and beams. We call them tie columns and tie beams. So the main reason, the only reason of providing these tie columns and beams in this case is to confine the wall. So if you have seen the failure of these masonry infill walls, they fail in the outward plane direction. They develop a lot of cracks. So if we can somehow reduce the free span of this wall, then we can reduce the damage. So this is exactly what we do by providing very small sections of these tie columns and tie beams. Look at here, the sections are very small in case of confined masonry. So we just tie these masonry walls together using these tie columns and tie beams, and that is their only role. There is no ductility in these tie columns. There is no design. It's only thumb rules. So this is the size. You just provide 100 mm by 100 mm or equal to the thickness should be equal to thickness of the wall, and then just provide 3 to 4 bars of 8 mm to 10 mm reinforcement. Very simple. And we sometimes provide this toothing arrangement. So toothing means you can see here the individual layers of these bricks. So they are going inside. The concrete is going here into the wall, right? So such kind of arrangement increases the bond. Okay, so this is a very simplified system compared to the masonry infill RC frames, but then the performance is comparable. And why is it comparable? Because we are using the material to their capacity. We are wasting infill here, but we are not wasting here. Let us see what we have done. So we did a similar study like we did for Assam type housing. So this is how we construct these houses. I'm showing you this construction for a specimen with aspect ratio 2.0. So this is a very slender specimen. And you may argue that where do we find these slender walls? Well, like I said, that the primary objective in confined masonry walls is to reduce the free span. So I'll show you some photographs where the because of presence of walls, because of presence of openings, you may have such slender wall specimens. So walls are constructed first. Concrete is poured in the tie columns and tie beams later. So this is the constructed specimen, and we did testing. And let me see if you can see the video here. So this is a half scale specimen, very similar arrangement where we apply the lateral displacement using these actuators. And here you can see the lateral drift that is being applied. And you can see how the cracks are forming in the masonry. And like as we already discussed, these cracks actually form because of dissipation of the energy. Okay, so this is where because of sliding, because of uh, the interaction between the frame and the masonry, the energy is dissipated. So you can find at drift level 14 some failure in the masonry, failure in the tie columns as well. Okay, so from a distance, it appeared to be a very similar construction like masonry infilled RC frame, but their behavior is completely different. Even their design is completely different. Here we design the masonry wall, but in case of RC frame with infill, we design the RC frame. And rather, I'll say we misdesign the RC frame. We don't do that properly. So that is why this system is coming up. So if you don't want to design the reinforced concrete properly, then let us design confined masonry. Let us construct confined masonry walls. So this is the comparison before and after test. What happened? What kind of failure was that? This is aspect ratio 1.5, and you can find similar damage. Aspect ratio 1.0, which is a squat frame. So you can see here that the damage was more or less concentrated in the bottom side of the wall. Now, interestingly, this work was carried out by your own alumni. Bonisha Bora is a 2014 batch from Royal Global University. She is doing this work and she has almost completed her PhD now. Within a few months, she will be able to submit the thesis. So the whole point of discussing all this is these are very simple systems and these have been proven to be performing really well during earthquakes in several countries. For example, Chile, in which big earthquakes are really common. There are thousands and millions of such buildings which have performed really well during the earthquake. In India, we construct these buildings, but without realizing that these are confined masonry. So, some little bit of things that we can do to improve the system, we are not doing that. But once we realize that these are confined masonry buildings, we can actually improve the system. Fine, then I've shown you two solutions that we can adopt or at least smaller buildings. So in summary, the problems that we discussed are not specific to Assam only. But then this is not something that we should feel happy about. That it is like मैं तो अकेला नहीं मरूंगा, सबको लेके मरूंगा, right? So this is not something that we should be feeling happy about. The main question is why recently constructed buildings are damaged during earthquakes. And you will find hundreds of stories where people will say that old buildings are performing well, but that the recent buildings are performing poorly. So it has, of course, it has something to do with the poor material, with poor workmanship, with poor labor, and with poor engineering judgment. Look at this building. It was constructed in 2015, and within a few months, the Imphal earthquake struck, and these people had to demolish this building completely. It was a hostel building for the Sports Authority of India, and people were staying during the earthquake, 6.78 magnitude earthquake. So huge damage to this building. Of course, it could have been retrofitted, but then the government decided that they will dismantle it within a few months of construction. Again, another open ground story, four-story building, Imphal. Immediately after construction, and you can see here that the construction was actually in progress in the top floor. But there was huge damage here to several columns during the earthquake shaking. And you can see what type of construction is there. So here you can find that this is the beam, these are the columns. And because of some funny reasons, people actually make bigger rooms on the top because they think that here they can save some money, some FSI criteria, which I don't understand. And then when they go up, this area is further increased. You go up, this area is further increased. So as you go top, you have reverse pyramidal structures, right, which is very interesting. And you can see what type of opening is here, what type of opening is here, completely different. Here they constructed an opening here without even understanding what can happen to this building. A very simple market building, the famous Ima Kettle market in Imphal, and huge damage suffered because of, and it was also a recently constructed building. So why workmanship is so poor? Because we want to save money. Why seismic codes are not being followed? Because of course we want to save money, we want to save time. We don't have skilled people who can actually understand the codes. And this is what we do then in seismically active areas, in seismic zone 5. If we are providing the spacing of the stirrups at about 150 mm, then we expect damage. There is no way we can prevent the damage. Look at the clear cover here, a clear cover of about 125 mm. Of course, there will be damage. Then we have found some very great ideas that people use for having some scope of future construction. They leave such kind of bars, right? And you can imagine what will happen to these bars during change in the weather pattern. They all will be corroded in just one cycle of the weather. And even greater ideas that they provide even the complete reinforcement detail bars, the cage, and they construct later. I'll show you this photograph here. This part of the building. What was done here is that this joint was not there originally. And it's very obvious because you can see the beam column joint is here. But then the owner wanted this beam here. And the only way it can be done is by exposing the main bars of this column and then connecting these bars of this beam to these columns. What a great idea. And then they will say that their building has failed, has fallen during the earthquake. What else it can do? When will the chalta hai attitude end? Then will our buildings will be safer. How that will happen, I don't know. But then here is a very interesting example of how we are obsessed with beautification, with beautiful look of the structure. The drain water pipeline has been provided inside the column. You can see here, this is the PVC pipe which is provided inside the column. So it is such an important idea to have good aesthetics, right? That we even are ready to sacrifice the quality of the construction, the strength of the structure. We don't bother about it, right? If you go to any developed country, you will not find any plaster, right? But here we are very fond of plaster because we can actually uh, show that the construction is really polished because our real structure is not polished. Are the soil always responsible, poor soil, for the structural failures? For example, here, this was under constructed water tank. No load at all. There's no load here, right? But still, you can see here that it tilted during the earthquake shaking. Now, because there's no load, the question I'm asking, is the poor soil only reason? The answer is no. It is not the poor soil that is only responsible. It is us, the structural engineers, the construction workers. The supervision was very poor. We knew that the soil is poor, so what did we do about it? Nothing. Now, this is a very good example of this chalta hai attitude, of this engineering judgment that we sometimes don't use, of the design that we carried out, of the detailing we use. This is a very simple structure. This is a gate of a university in Imphal, right? And this gate has no load other than its own self weight. And look at it, what it has, how it has performed. This is not a very complex structure to design, but only because of our chalta attitude, such structures are failing. And we can now think of what will happen to the bigger structures. So this is the lesson that we learn. So are we not aware of the hazard? Why are we doing this? Are we pretending that all is well? Well, of course we are aware of the hazard. So I could see this very old painted wall in the city of Imphal after that earthquake. So they have written here that what to do during an earthquake, what to do after the earthquake, right? So people know it, but then because these events are not frequent, we somehow don't pay much attention to that. So the finally the I would like to summarize here that if we can't construct these RC buildings properly, then I think it is time to adopt vernacular housing systems like Assam type houses, confined masonry houses, at least for smaller family dwellings, if not for bigger houses. Design codes are must. Even if we go for these vernacular housing systems, we have to develop design codes for them. We cannot simply leave it to people to just construct as per their wish. Good material and workmanship, there's no alternative to that. And finally, we have to be ready and be prepared for the next shaking. We cannot predict when it will happen, but what we know is that it is going to happen. So thank you very much uh, for patiently listening to me, and with the hope for a better construction, I end my presentation here. and I would be very happy to interact with you to answer any question if you have. Thank you.
Thank you, Professor.
Thank you, sir, for delivering such an elaborate and informative lecture.
Thank you, Professor.
Yeah,
Arnav
thank
Sharma,
you.
sir, do you like to
On
add
behalf of the Department of Civil Engineering, Royal Global University, I thank you for your excellent delivery. But then I have a small question, sir.
Yes.
The question is, even now in my house, I have a team of workers working. Now, as of now, we do not have any stipulations for the contractors, whether they are trained, whether they know seismic design, whether they are aware of the codes, and the people they deploy on site. Now, this is one major issue. Now, GMC and GMDA, the permission granting authorities, they give you a permission without having any knowledge of the team that is going to work for construction of the building. Now, this is a major issue that we are finding. Even if we have got the SDBR report, structural design basis report from a certified engineer, but then on site, whether these workers, whether they have got some qualification to construct such a building or not, that has never been verified. That is never verified.
I completely agree with you. Yeah.
So that is a major issue. That is a major issue, and we hardly have any tap on this. And this is something which I probably have discussed in many fora, and I understand that if this issue is resolved, and if we set a certain amount of qualification for these workers, then many of these problems can be eliminated at the site itself.
Correct.
Yeah. What is your
In
take
fact,
on this, sir?
yeah. In fact, ASDMA, the Assam State Disaster Management Authority, actually did a very elaborative training of these masons and workers, and they provided the certificates to them. The idea was they will train the head masons, and who in turn will train the other laborers, the second grade masons and the laborers. Now, the first criteria was fulfilled. I think they trained a lot of head masons, but then I'm not sure what happened after that, how the chain broke, because there are a lot of people who move around a lot. So sometimes they work on this side, sometimes they will leave Assam, they will work somewhere else. People from outside will come here. So it's actually really a very difficult scenario. I completely agree with you that it is this is where we need to actually work hard and think how we can improve this the quality of these construction workers.
Thank you, sir.
Sir, now we'd like to raise some queries. That is, one query is from Mr. Shubham Kashyap. He wants to know what is the maximum probable magnitude of earthquake in Kopili Fault.
Well, I'm not a seismologist, so I'm not sure uh, how big earthquake this Kopili fault is has the potential to struck. So, but how does it really matter? It is not only the Kapili fault that is there in this region. There are many faults, many fissures where these earthquakes can occur. What is more important than pinpointing or shortlisting some faults? The more important point is to be prepared. So earthquakes can occur anywhere in this region, right? So even after 120 years, we don't really know where exactly this 1897 earthquake took place. Where is the epicenter? We don't know. Some people say it was near Shillong. Some people say it was near in somewhere in Assam. So it is not really important how much potential this Kopili fault has. Other than academic interest, of course, people do research. That is also very important. But as a common person, as an engineer, I'm not really interested in how much is that. Of course, if I want to do seismic microzonation, then of course I will need this information, right? But then, as a researcher, I will be worried about this. But For design issues, I will presently, as of now, because we don't have seismic macrozonation ready, I'll more worry about the quality of construction entirely in the state of Assam, rather than just having better structures near Kapuli Fault.
Right, sir. Well, one more question we have is from Miss Antara Banerjee, madam. She wants to know how to meet the needs of rapid urbanization, especially in cities like Guwahati, with the concept of vernacular system of construction, sir.
Yeah, very good question. And this is a very common question that people ask me whenever I give some presentation of where I show my interest on this vernacular housing system. See, we should not think Assam to be Guwahati only, right? Guwahati is just one city in Assam. How many people live in Guwahati and how many people live in Assam? In Guwahati, I'm not saying that you go for vernacular housing system. The entire city is converted to vernacular housing. No, that is not required. But also, it is not essential that every house in Assam should be constructed of reinforced concrete, right? So that is my point. In city like Guwahati, where we can have good engineers, where we can have good material, where we can have skilled labor, we should always go for reinforced concrete or steel structures, properly designed. High-rise structures, there is no problem with that if we can do that properly. But my point is, somehow we are not doing that. And for smaller structures, we are not at all doing that. For two-story houses, three-story houses, even single story, nobody designed these buildings, right? It is only the head mason, some people who using some thumb rules, they only construct these houses. So my point was, can we not construct these houses using these vernacular housing systems? What is the need of reinforced concrete?
Right, sir. Sir, can you just suggest whether this soft story, like soft ground building, that problem can be retrofitted using bamboo bracings if we replace it with the steel bracings?
Uh, it has to be studied really how effective these bamboo bracings will be in case of reinforced concrete structure. I have seen bamboo bracings being used in wooden houses. So they really improve the structural system. They really improve the performance of wooden houses. But then the issue with the reinforced concrete structures is slightly different. There will be a big question on how these bamboo bracings will be connected to the joints, the reinforced concrete joints, right? So there are issues that need to be studied more. So without study, it is actually difficult to comment on this question. But good question from Rishikesh, I think, is your faculty colleague. Time to go for PhD.
Yes, sir. Right, sir. Sir, in the beginning of your presentation, have shown a building which is it is in North, I think so. So, a structural engineer, sir, what can be your possible suggestions to like withstand the building, or to what suggestion do you prefer for the building?
Yeah, yes, very interesting again. This building is, I think it is on the main road. So we can see what happens to this building. We can see how, what have people done, whether they have dismantled the building. It is not essential to dismantle this building because there is no other damage. Nowadays, we have anchoring system, we have systems which can actually lift the entire building, and then we can retrofit the foundation, we can improve the foundation, we can improve the soil, and we can again bring back the whole building to its original state. That is perfectly possible. The only question is whether these people will be able to spend that much amount of money or whether government will help them. I'm not sure. So we'll have to see, because I'm sure people will post their photographs, and if you find it out what happened to that building, I'll be really interested.
Thank you, sir, for your valuable time and effort that you took to share your knowledge with us. We also wish to have your presence in our university as soon as the pandemic is over.
Sure, sure.
We'd
Thank you.
really be happy to have you in our campus. I would like to extend my vote of thanks to Dr. S.P. Singh sir, Dr. Alok Kumar Borogohai sir, Dr. Arnav Sharma sir, senior faculties, my colleagues, and all the participants for joining the webinar. Hoping to see you again in the upcoming webinar. Till then, take care, stay safe. Thank you. Thank you, sir.
Thank you very much.
Thank you, sir.